what I'm going to do is demonstrate in detail how to build a polyphonic granular synth engine in Pure Data. And then after we've done that, that'll be a fairly lengthy and detailed process description. And then we will build a graphic user interface for a tablet or iPad using MobMuPlat. But first things first, we want to, for demonstration purposes, get a audio file into Pure Data. We use the open panel object in conjunction with, let's zoom in. Yeah, we need big font there. Open panel object, and to it we will connect the sound filer object. We need to go via a message. See, read resize. So connect a message to the open panel, say read, then the argument resize, so that the buffer is resized to accommodate whatever audio file we put in there. And $1 is just the variable that open panel passes to that message, which is the name and location of the audio file. And we're going to read into, let me see, I'll call it SF buffer, sound file buffer. Now I need a buffer. In this case it is table read or tab read. Did I use tab read 4? No, just a straight tab read. Tilde, since it's an audio object, and its name is SF buffer. So pass that message into sound filer. This OS is getting very old. Very old indeed. Come on, see, it's just hung there. Okay, there's my buffer. No such array. Yes, well, I've just corrected that. SF buffer. And I don't need to connect that tab read to anything yet. So now I need bang to open the dialog window that lets me go and look for an audio file. Oh, and let's put an array as well. And I will call it name SF buffer. There we go, we get a little visual representation of our audio file. Hit the bang, go and find an audio file, and I'll just use a drum loop. Properties, let's have polygons instead of dots, and that's our audio file in tab read. And I think I can open him. No, I can't. So this tab read object will read from a buffer that contains this audio file that I've just put in it. Now, how do I read from it? We need an incrementally rising signal that gives the location in samples in the buffer. And the object that we commonly use for that is a phaser. And let's give it a frequency of, say, 0.5. That is going to ramp from 0 to 1 every 2 seconds, or a frequency of 0.5 Hertz. Good heavens, why does this keep hanging? Do I have anything else open? Nope, doesn't matter. So it's going to ramp from 0 to 1, so that will read the first two indices or indexes of this tab read. But its size is not between 0 and 1. It's between 0 and whatever the total number of samples are in that audio file. So I'll just open that drum loop again. 124439, 124,439 samples. How long is that in seconds? Well, we can do some maths to find that out. But for the time being, what I'm going to do is multiply that 0 to 1 ramp, multiply tilde, and just copy 124439. That's the total number of samples in that audio file. That's what tab read needs. And let's make a DAC, digital audio converter. And what's happening? We need to convert samples to frequency, and let's just stop that for a second. So clearly the frequency of the phaser is wrong. The size is right, but the frequency is wrong. And I'll just remind myself how we convert samples to frequency. It's sample rate divided by the number of samples. So if I use an expression object and say 44,100 divided by the number of samples gives me frequency in hertz. So 124439, 124439. So I was close with my frequency, but not correct. It's once every, no, 3 seconds long. So the audio file is 3 seconds long. 0.354, 0.354. There we go. We're reading from an audio file at the correct speed and for the correct duration. So the second video, what are we going to do, or the second part, the part that's coming up, this is just a test video. What we're going to do is read a slice from the buffer. So we're going to read a small portion of the buffer, and we're also going to allow control over from where in the buffer that slice is drawn. So we'll start at 0 and have a small slice, but then we also want to start at other places, retaining the size of that slice, and that's what we're going to do next. So this is where we left off last time. Look, we are going to just remind ourselves what we're doing. So we're simply reading an audio file using these objects, and the two numbers we're interested in are the length of the audio file in samples and then the frequency of the phaser that's reading through tab read. So we give our phaser a frequency. What sound filer outputs is the size of the file, the audio file, in samples. To convert the number of samples into frequency, we simply divide the sample rate by the number of samples. $float1 here, and that gives us a frequency. But one thing I did neglect to do is that after reading the help file for tab read, we read that a signal at the left inlet will move to the corresponding index in the table's array. The index ranges from 0 to the size of the array -1. So the number of samples, we simply subtract 1 from that value to get the correct number of samples. Let's just reinitialize that at 12, 44, 39. And there's no great audible change, but we're now dealing with correct numbers. So what we want to do, or what we're going to do now, is slice the audio file, read a very small chunk of the audio file. And there are a number of maths issues that present themselves, primarily because the number of samples is arguably less intuitive than a millisecond value. We do tend to think, or many of us do tend to think in an audio file as having a duration rather than a number of samples. And furthermore, if you want to move about through an audio file, when you're talking about number of samples, you're dealing with very large numbers. So arguably, it's more intuitive to use a millisecond value. It presents a number of challenges that we're going to solve now. So I want to use millisecond value here as an input to all this, these two values. Value 1 being the frequency of the phaser that's reading, and then the size of that phaser ramp. And to convert milliseconds into samples, we multiply the millisecond value by 44.1, which is the number of samples in a second, 44,100 divided by 1,000, which is 44.1. This gives us the number of samples, and then to convert back from samples to milliseconds, we simply reverse that equation, which is number of samples divided by 44.1. Let's just test that. Let's say 2,000 milliseconds. That's 2 seconds. So we get 88,200, which is 44,100 times 2. And then divide that by 44.1 and we're back to 2,000. So we have all the maths we need. Milliseconds to samples is this, and samples to milliseconds is that. And then finally, if we do one more expression object, oh, hold on, sorry, Control E, an object, if we do expression 1,000 divided by that number, we get frequency, I do believe. So 2,000 should say 0.5. Oh, sorry. Not really concentrating. Control E. 2, 1, 2, 3. Donk. There we go. Milliseconds to samples, back to milliseconds to frequency in hertz. So all the maths we need. So first and foremost, I need to convert milliseconds to frequency. We've seen how to do that. Add an object, expr tilde. Lets us perform maths on signal vectors. So 1, 1, 2, 3, 1,000 divided by, and because we're in the signal domain, we don't say $float, we say $vector1. And that gives us, come on, it gives us frequency. And now we also want to convert milliseconds into samples. And we do that with another expression, tilde object. And we say $vector1, $vector1 multiplied by 44.1. And the reason I'm recording this via my tablet is because sound card issues and microphone issues and screen capture issues. So let's remember to do minus tilde, subtract 1 from the number of samples, and E. Let's say 124439 into samples. And that gives us the duration, which is 2821. 2821. Enter. Cool, it's working. Let's try, that's 2.8 seconds. Let's try 1 second. That's 1 second of the audio file. Let's try half a second of the audio file. You can see where we're going with this. I'm going to keep this convenient converter here. Just put it down out of the way. This is all the maths we need to convert samples to milliseconds to hertz and back to front and upside down. So you can see and hear that we're reading from the start of the audio file at a given size. So let's get some labels in here. Millisecond size. This is the size of the loop, we can call it now, or slice. This value here is samples, sample size, oops, to S-I-Z-E, sample size, and one more comment, just to keep things crystal clear, this is our frequency. How can we move through the audio file? Well, remember that the phaser is ramping from from 0 to 1, and then we're multiplying in samples, because that's tab read wants an index in number of samples, or location in samples to read from. So we're going from 0 to 1 here. Well, the solution is to add an offset plus tilde. So at the minute, the phaser is ramping from 0 to 1. I'm adding nothing to it, so we should hear no change, because we've added nothing to 0 to 1. Let's try adding something to it. Now what I'm going to use is not a signal object, I'm going to use a line object just for the moment. I'm going to pack two values. Line wants a value and duration to ramp to that value. 3 is a number. So what's happening here? Remember, we're dealing in samples at this point. So we're going to, instead of ramping from 0 to 1, it's going to ramp at least this phaser before it's scaled by the correct size that we want. It's going to ramp from a number to that number plus 1. And then it's amplified, scaled, mapped to suit our needs. So we're still talking about 500 milliseconds ramp. So instead of this phaser now ramping from 0 to 1, it's ramping from 1 to 2, and then multiplied by whatever the sample size is. So we're moving through the audio file. Drum loop probably not ideal. Let's pick some spoken text, spoken word, sorry. So let's hear that. Let's just mute that, go back to our calculator here. We've 125454. 125454, that's the number of samples in that audio file, and it is 0.351. Oh, how do I get 351? I'm going to have to guess. It's about a second long. 1, 2, 3. Is it? Oh, I don't want an offset. 2, 1, 2, 3. 2, 1, 2, 3. It's bigger than that. It's about that. So that's half a second. So let's try 250, quarter of a second. So we've got a slice and we can move through the audio file. And what you can notice is that because I'm smoothing this value over time, as we move forwards or backwards, you can hear what's commonly called the Doppler effect, because we're moving forwards and backwards in time or over time. We don't want this value passed to the offset as a ramp, without belaboring the point. What we can do, oh, I shouldn't have done that, Z, get rid of that. We only want to pass that value when the phaser has reached the end of its ramp. So it's going to ramp up, immediately return to 0, and start ramping again. And it's at that precise point in time that we want to pass the value to the offset value. And the way we do that is via sample and hold. We use the phaser ramp as a trigger, at the end of the phaser ramp as a trigger. And now we can get rid of that and just call this sig tilde. But I want to pause first of all, because we're dealing in samples and milliseconds conversion. I want to input millisecond values here, and convert it to, I want milliseconds converted to samples, and we can do that again by multiplying by 44.1. Multiply tilde 44.1. We've got a quarter second slice, and another comment. This is going to be milliseconds offset. So we'll listen. So it's getting a value of nothing at the minute. So what have I done wrong? Oh, of course. Yeah. Silly boy. Yeah, let's go there. Okay. So I can read through the audio file, but what your ears probably may or may not pick up on is clicking. There's definitely a click there. I'm using sample and hold to pass that value only when the phaser ramp reaches its end, but I'm still getting clicks, and that's because we're not reading from the start to the end. We're reading from an arbitrary point to another arbitrary point, and then folding back to that same arbitrary start, arbitrary end. And those sample values will not, 99.9 times out of 100, will not be the same. You'll get a read discontinuity, which is where the clicks come from. How do we solve this? I can change the size of the grain. I can move through the audio file. But I'm getting clicking, and we want to get rid of those clicks. How do we do that? Let's get our input controls up at the top here, the stuff that we're kind of going to hold on to. How do we get rid of the clicks? Well, the common granular method is to make a little curved window. Nice little curved window. So that at the start of what we're going to call a grain now, or a very small slice, the amplitude is at 0 and it smoothly ramps up, lets us hear the grain, and then smoothly ramps down again. So we're hiding that discontinuity. And the way to make a window is we're going to use the phaser ramp, and we need to convert it. Now this, I'm using pure data, or PDL2org, and it comes with an object that you don't get in vanilla PD, as far as I'm aware. Scope, akin to the spectroscope, I think it's called in MaximSP. So there's our ramp. Let's, just to help visualize things, let's make it larger. So there's our 0 to 1 ramp. I want to convert that into a window, and in vanilla this isn't per date, this isn't PDL2org specific. We get a cause object which converts numbers, straight line numbers, into a curve, cosine. There we go, like that. But the cosine domain is -1 to +1, and as it turns out, it's also out of phase. I won't belabor the point, but what we need to do is shift this cosine ramp 180 degrees out of phase, and we also need to change its domain, which is currently -1 to +1. We need to change it to 0 to 1, because it's our little amplitude ramp that's going to hide the clicks. And we do that using two maths functions. The first being, this is the way I do it, multiply it by -0.5. That shifts its phase and rescales it to between -0.5 and +0.5, and then to that we simply add 0.5, and it brings us back to the 0 to 1 domain. And a nice little, I'm going to zoom in just for the camera there, nice little curved window. And then our final output from tab read, we multiply the output by that window, and our clicks have disappeared. But as is always so often very true in life, doing that solves one problem but then creates another. So we're getting no pitch modulation thanks to the sample on hold trick. Yeah, I'm fed up with scrolling that number box. We're going to use a different method to read through the audio file. So there's a handy little object, horizontal slider. It's kind of more intuitive. And what I want to do is set its range to between 0 and the number of samples. And we do that with a message to the slider called range. I think it's called range. Yes, it is. We want to go from 0 to whatever the number of samples is. And I'll just use a send object. So send samp size. $1 receive samp size. Because I'm using such a large font, we're starting to get cluttered here. Put this off to one side. And now, if I reinitialize that sample value, which is 125454, 125454, that doesn't seem to be doing anything. What have I done wrong? Ooh, that doesn't look too healthy. Properties, that's it. Or width, some of these. There's no range there. Okay then, let's go to the help file. Setting slider properties through messages. Range $1, $2. Ah, okay. That's why. 125454. Oh yeah, okay, so just a couple of corrections there. In this message I had $float1, it just needs to be $1. And now that I'm using samples instead of milliseconds, I'm using sample size directly. I just need to get rid of that multiplier. I said milliseconds were more intuitive, but this slider now is set to the size of the audio file. So I can graphically slide through. Samps. Let's make a small grain. So, just to recap, what are we doing here? Let's just mute that, because there was a lot of improvisation there and a couple of errors. Certainly a little lack of clarity. So just to rectify that, the number of samples in the audio file is being used to set this slider between 0 and the end of the audio file. And I'm passing that to an offset value So my phasor is ramping from 0 to 1. I multiply that by the number of samples given by millisecond size. So I'm no longer ramping from the start of the audio file to the end. I'm just choosing a changeable size or a variable size. And without this offset value, if that wasn't there, I'd always be reading from 0 to whatever size the slice is. But now that I've added this offset value, I can shift that shift that slice forwards through the audio file. Let's listen to that. So this is 200 milliseconds from the start of the audio file. This is a 200 millisecond slice halfway through the audio file, a quarter of the way. Let's make the slice smaller. Let's say 100 milliseconds, a tenth of a second. So there's obviously silence at the start of the audio file. So we're starting to draw nearer to a granular synthesis engine. This is all good. Change the grain size. There's a 30 millisecond grain. Well, the problem is that we're getting what are commonly known as amplitude modulation artifacts. Remember, we're using a little grain window, a curved window, and what that is doing in effect is silencing the slice, raising its amplitude, and then silencing it again in a curve. And if you do that duration of less than around 30 milliseconds, what you're effectively doing is amplitude modulation. And that reveals itself as a tone or spectral artifacts. Let's try a smaller grain. There's a pitch. That's it. And 1000 divided by 20 is 50, so that's 50 hertz. I didn't get the octave right when I was singing it, I'm sure, but we don't want that. How do we fix it? So we're back in Pure Data to see how we can fix the amplitude modulation artifacts that I was talking about a few moments ago. So I'm going to load an audio file again. Let's stick with Cherokee. That's 90 milliseconds. Let's get down to a smaller grain. Let's try and get that 50 hertz. Or sorry. There's a ghost frequency that's not present in the original file and is a result of amplitude modulation at audio rate. This phasor is running at 50 hertz. Anything over around about 20 or 30 hertz is going to create ghost frequencies or spectral content. Okay, just silence you for the time being. So I had promised a solution, and the solution is this. What we're going to do is so far we have created a nice curved amplitude window for the grain, and its purpose was to hide the discontinuities between the start of the grain and the end, the sample discontinuities, effectively the difference in sound. And the way to, or one way to ameliorate these amplitude modulation artifacts is to create a copy of this element, the reading, the part that's doing the reading, the window, and overlap it 180 degrees out of phase, or offset by 50%. So as one grain window is rising, the mirror is falling, and as that first one is falling, the second one is rising. That doesn't remove the amplitude modulation artifacts completely, but it does go some way to decreasing them. So we still have one phaser, and this is kind of key. We're relying on one phaser so that we're more or less sample accurate throughout the algorithm. So the first thing to do is add an offset to that phaser of 0.5. It ramps between 0 and 1. So if we add 0.5, we're now between 0.5 and 1.5. But we don't want that. We want to wrap it. WRAP, oh, not capitals. Where did I get capitals from? WRAP tilde, which effectively shifts that phaser ramp 180 degrees out of phase. While this one is at 0, this one is at excuse me, 0.5. Now we just need to hook up. So first of all, he goes to our cos window, then he goes to our multiplier, then he goes to sample and hold. And what comes in? Well, we want the size of the grain, and we also want our offset. So it's getting a bit spaghetti junction down here. We'll be tidying things up later. So effectively, this is our offset phaser. This guy here, the plus tilde and wrap. So we've duplicated that, and let's see if we can prove it. Delete, and what I'm going to do is create the mixer or summer plus tilde, so these two windows get added together. So there's one. What have we got? And let's get rid of that. So that is a phaser running at what's that? 80,000. That's 12.5 hertz. A grain of 80 milliseconds. And let's listen to this other one. Sounds exactly the same, but it isn't. It's offset by 50%, or 180 degrees. So what we have now is two grains, one at 80 milliseconds and another one at 80 milliseconds. So I guess you could say that we have, for the price of one, we have two 40 millisecond grains, and their windowing functions are 180 degrees out of phase. I think that's all I need to say about that. Not bad. Let's try 120. Now our ears are still picking up the amplitude modulation, but at least there's no ghost frequency content because the phaser isn't running fast enough. It's at 100 milliseconds. It's 10 hertz. Doesn't sound too bad. It's only really when this offset isn't moving. Yeah, let's go back down to 80. It's when we're static, or when this offset value isn't changing, that that robotic humming becomes more obvious. And with source material that's very transient heavy, like a drum loop, it's less obvious when we're reading through the file, but then it's even more obvious when we're static. You know, it's like you can't win. Yeah, that doesn't sound frozen, that sounds like a small loop, which is what it is. Let's try 60. You'll find yourself doing this a lot, messing about with values to see what the trade-offs are. Now that sounds good to me when we're reading through the file. But when we're static in the file, that loopy buzz, that's the technical term, becomes more apparent. And here's a common solution. What we're going to do is we're going to add a noisy blurring parameter to this offset so that the grain isn't static in time. This offset value that we're adding here and here, as you Control E, we're adding here and here, which comes from this signal object here. We're going to add noise, tilde, and we're going to first of all scale that noise value up, I think. I can't remember. Let me see. I just need to do a check on something else I've been working on. Yeah, we're going to scale it up and then low pass filter it. Scale it up by a factor of, let's say, 50. And then add a low pass filter. A really aggressive low pass filter. Then Control copy, Control verify. I'm going to use this as a scalar. So at the minute there's nothing coming out of here because I'm multiplying it by 0. I need a number in order to control the range of this noisy offset. And to make things easier, I'm going to raise it to the power of 2. We'll see why in a minute. So this is the value that I'm going to add that blurring factor to. So I need another multiplier. No, not a multiplier. Plus. Yes. It's a noisy offset. And if I just plug that in, it will have no effect because we're adding nothing. Ooh, we're adding nothing to that offset. I don't know if your ears can pick that up, but as I said, when we're moving through the audio file, we're reading at this small grain size. We're effectively 60 millisecond grain slowly moving through the file. The spectral artifacts aren't that obvious to my ears anyway, but when we're static, when we're not reading through the file. So let's see if I can tidy this up a little. Just want to maybe drag all this, oh no, drag all that. Maybe try and tuck him in there. This is our offset. So let's have a listen now to a static grain. Once I get up to about 200, and once again it's probably best to use spoken word just to get an idea. So we're at the start of the file. I'm way, okay. Let's raise the noise offset we're adding. So it's catching the start of it. We're getting way, so that's quite a large noise range. It's not really intuitive, this value I'm inputting here, but so sue me. Let's get a static grain. So we'll set the noise offset to 0. There's shh. Let's see if we can get that SH sound. So you should hear that we've got some blurring now. So rather than the two grains being completely static, they're oscillating around this point in the file. Let's listen to playback. If my operating system would keep up. Not great. Let's go back to 80. Oh, I just want to try something. I'll do this on camera rather than off camera. I'll go up to 500 grain size. Okay. Because my maths is terrible, embarrassingly so, I'm going to have to rely on the scope object for this. So that's my little grain window. What if I raised that window exponentially? Would I get steeper sides? It's actually spending more time closed than it is open. Yeah, I may edit this out. Yes, I did have to pause while I worked things out here. So let's get back onto this window. Originally we have, well, a 0 to 1 ramp from the phaser. We take a cosine function of it, which puts it in the domain -1 to +1. And previously, all I was doing was multiplying it by -0.5, then adding 0.5 to it, and using that as my window. But a cosine spends an equal amount of time descending as it does ascending. And what I wanted to do was fatten that cosine curve a little. So we raise it to a power. But what happens then is that it spends more of its time in the off position than it does in the on position. So it's down here, and then it ramps up quite quickly and ramps down quite quickly and spends too much time at 0. So the cosine window is too small. So if we subtract 1 from that, what we do is invert it and also conveniently phase shift it. So instead of multiplying by negative 0.5, I multiply by 0.5. It's still out of phase here, it's still out of phase here, it's exponential here, and then that value subtracted from 1 conveniently flips the cosine window, which means it's spending more of its time open than it is closed. It's spending less time closed. That's the key goal of this wordy algorithm. So 1 subtract that value does 2 things. It flips the window and also phase shifts it by 180 degrees. And I'll prove it. And then I'm going to hit pause once we've done this, because it sounds really nice. Okay, one other thing we can do, I'm going to do now, is I use a send object, but I'm going to send to SF buffer. So this allows me to make a wireless connection to that buffer, and I'm going to send, there are 2 messages that are often handy. The first one is Normalize, which does what it says on the tin. And later on, much later on, we're going to be making use of a constant, and we're going to send a constant to the buffer. Why? Well, we'll find out later on. So normalize, boom. There's a lovely little pizzicato violin here. Sounds very amp mod, doesn't it? That's because we're only listening to 1 grain. Here's the 180 degree out of phase one added to it. And because I've raised them exponentially, the grain is going to be open more than it is closed. And you can see I've got a little bit of noise here. Let's set that to 0. That sounds a little robotic, but just a little bit of noise helps to smear the grain window in time. I think that sounds really nice. Let's look at something else. Let's do jongly again. He's quite loud anyway. Doesn't need normalized. Let's raise this noise range. And now we're starting to get grainy. Bear in mind, we are only using 2 grains here. That sounds pretty damn good for just 2 grains. Normally we would make this engine polyphonic and smear grains 8, 12, 16 for some real buttery goodness. But this is just 2 grains. Wow. So that's the end of this section. What I'm going to do next is add a pitch control. We have no control over the pitch of the grains, and I want to do that next.